So once again, welcome to a new problem. This time we have a box that's laying on a surface, and the assumption is that the box is being tilted a little bit at an edge. So this is a special edge for the box. Um, it looks upwards. Well, it's a slight tilt, so we don't want the angle to be super steep. Maybe something like that. So the box is tilted like that and like that. There is a specific height. So maybe this tilt is super steep. So we want to just make sure that we don't go overboard. Maybe something like, yes, something like that, and then that, and then that. So this is a box that's tilted, and there's a force acting and trying to push it to tip. And that force is acting at a specific height, which we're going to call H. Critical in solving the problem. The center of gravity, CG, is right there on the box, and the weight of the box, mg, is going to be acting on that portion. At this edge, there are two forces acting. Obviously, the normal force, Fn, that opposes the weight, and also there is a frictional force, which we're going to call FFR, almost trying to stop the box from moving. The width of the box is 1.0 meters, and that means half of the box is going to be 0.5 meters, half of it from the weight. The height, the entire height of the box is 2.0 meters. So that's the information we're given. We can kind of like think about the box before tipping. It has a weight right there, and then there's a force pushing it, F, towards the right. So this is a special location right here with Fn and F, frictional force, and the normal force that opposes the weight. Remember, action and reaction forces are equal and opposite. The entire distance, this height is h. This entire height is 2 meters. This one is 1 meter. And then halfway through is 0.5 meters. Just for clarity, and there are two things we need to solve for this problem. The weight of the box, mg, is given as 250 newtons, and the coefficient of static friction is given as 0.60. So we want to find what's the minimum F. This force is F right here. So in part A, what's the I don't understand. I'm saying what's the minimum F of force required? What's the minimum force required to make it slide? That's what they're asking in part A, and then in part B, what's the maximum H that the force can be applied without tipping, or if you want to call it flipping. So those are the two parts of the problem. The system is in equilibrium, the box is in equilibrium, so the sum of torque around any point, most probably we're going to take it around this edge, but the sum of torque around any edge is 0. And then the sum of forces in the x is also 0, and the sum of forces in the y is 0. So we're going to focus on the sum of forces in the x being 0, and that simply means that assuming your positive is to the right and your positive is upwards, this is kind of like the y-axis and the x-axis, it means this force is pointing towards the positive, so F minus the frictional force is going to be 0. So the F has to be equivalent to the frictional force, which means that we'll just jump onto the next page to make it more presentable, which means that F equals to mu static friction times the normal force, Fn, which becomes mu static friction times mg, 0.60 times the weight, which is 250 newtons. And so this force, if you go back in part A, we're looking for what's the minimum force to make it. So the minimum force required for the box to slide is 150 newtons. That's the minimum force exerted on the box to make it slide. The next part of the problem is what's the minimum or maximum height? What's this maximum height before it flips? This force is pushing towards the right, so that means relative to the pivot or edge, it's going to be clockwise and therefore negative. The weight, which is going downwards, is going to be counterclockwise, therefore positive. And so those are the two forces we're dealing with. Sum of torques around the pivot is 0. So the positive will be mg times this distance. So this distance between mg, the perpendicular distance between mg and the line of action of mg and the edge, that distance is 0.5 because it's half of the entire width. So 0.5 meters minus F times H is 0. So that means FH equals to mg times 0.5 meters. So H has to be mg, 0.5 meters, all over F. So this becomes if we take mg was 250 newtons. So we had 250 newtons all over 150 newtons times 0.5. These two cancel. 5 goes here 3 times. 5 goes there 5 times. So we have 2.5. This is meters. So 2.5 over 3. And so when we divide those two numbers, 2.5 divided by 3, we get 0.83. So the maximum height before it flips, h, becomes 0.83. Just remember this one also is in meters, so 0.83 meters. Again, we used equilibrium. First of all, equilibrium in the x forces helps us solve for the force required to make it slide, F. That's what happens right here. And then we take equilibrium torque around the pivot. That helps us to solve for the maximum height. So I hope you enjoyed the problem. Feel free to send any questions or comments. and have a wonderful day. Okay, thanks. Bye.